Okay, come here. Let's get hooked up. Oh, did that not work? Yeah. Okay. Good. Okay. So I'm gonna stick right on. Whatever you prefer. I'll let you stick it. Perfect. So it looks like great sticking. Almost. Actually, I spoke too soon. You can also do this thing. Yeah, exactly. Perfect. Okay, I'm going to turn you on. Go, and then stick it in your pocket. Or whatever you. And you can.
These are awesome.
Good. Okay. Okay, hi everyone, welcome back. Now we are starting session 4, the topic of which is unveiling the ISM through the absorption of starlight. So we've dropped the scattering component, we're only looking at absorption. And we're going to start off with Timothy, who will be discussing topographic distance measurements of high velocity clouds with SDSS matter. Take it away.
Great. Thank you. So I'm Tim McQuaid. I'm a second year at New Mexico State, and I'm just going to be talking a little bit today about my work on measuring distances to high velocity clouds using stellar tomography. So I think as we've heard a little bit about this morning, high velocity clouds simply describe any large masses of gas that do not co-rotate with our galaxy and have high LSR velocities in excess of about 90 kilometers a second. And as we can see in this H1 pi map here, some of this gas may be in a state of inflow or outflow. It can originate from gas expelled via supernova feedback, gas secreting from tidally stripped gas, or precipitating from the CGM or IGM. But the essential thing about HVCs in our galactic evolution models is that they provide the long-term sustainability of star formation within our galaxy, since without this constant influx of gas on the order of half to several solar masses per year, we would, within the next few gig years, essentially run out of gas to fuel continued star formation. One key component, however, that emission maps like this don't directly convey is any information but the distance to these HVCs. And distance is critical because if you want to determine the mass and thus the accretion rate of these HVCs and how that'll impact our galaxy's evolution, the mass scales with the distance squared here. So if we want to properly constrain their impact on our galaxy's evolution, we need very precise distances. So the traditional way we do that is using stellar spectra. Essentially, as this cartoon illustrates, if we take a spectrum of a star and it happens to be behind our HVC, then we get absorption lines. Typically, we look for sodium-1 or calcium-2. However, of course, if our star is in front of it, then no absorption lines. So through a combination of detections and non-detections, we can begin to constrain the distances to our HVCs. So the one issue, but first, in practice, what this will look like is we'll typically have something like a 21 centimeter velocity cube here at the position of our star, and then essentially we can just label different components in velocity space. This is the sodium-1 doublet here. So first we just see our stellar component here, this absorption line. Of course, it doesn't really correspond to any peaks in the emission. We have our ISM, typically around 0 kilometers a second LSR, which we can see labeled here. Then all the way out here in emission, we have this little bump here, which corresponds to this velocity absorption component, and that's our HVC in this cloud, in this case, cloud G1. The issue with taking a bunch of high-resolution spectra like this, of course, is that it's quite observationally expensive. especially if you want to map out the full extent of these clouds, many of which can cover hundreds of square degrees. And I like to get a good night's sleep, not spend all my time observing. So wouldn't it be great if we just, I don't know, had a repository of many stellar spectra covering these HVCs? As it turns out, we do. This is SDSS-5, Sloan Digital Sky Survey, and in its current iteration, it's been conducting the Milky Way Mapper Survey, which one component of that is obtaining stellar spectra in optical with the BOSS instrument all across the sky. So we have all sky coverage. So I've plotted just the footprint of that over that HVC map. So from the north, we get that from the 2.5 meter at Apache Point. In the south, from the Las Campanas Observatory in Chile. So it's obtained at this point over 2.5 million stellar spectra all across the sky. And every single one of these, nearly every single one of these has distance estimates via Gaia and Baylor-Jones. So the one caveat with using these, though, is that the BOSS spectrograph is medium resolution, only R of about 4,000, when typically you need several tens of thousands in order to resolve those individual velocity components, the stellar atmosphere from the ISM from the HVC. So instead, what I've adopted is a stellar modeling approach where we essentially try to remove the star from the stellar spectrum. To do this, I'm using a suite of MOSSTAR models produced by my collaborator, Kay Rubin. These have been corrected in the calcium K line and sodium 1 line for interstellar absorption. So essentially, for those lines, it only has absorption due to the stellar atmosphere. That way, when we fit that to our observed stellar spectrum in blue here, take the residual, for those lines, we're just left with absorption due to interstellar and high velocity gas. So with that, furthermore, we also obtain the extinction for our stars. In fitting the continua, I apply just a Fitzpatrick extinction law. So we measure the extinction, sodium 1 and calcium K absorption for all 2.5 million of these BOSS spectra. I find about 250,000 of them have reduced chi-squares of less than 2. That constitutes my sample. So with that, I can share some all-sky maps I've produced. This is our extinction map here. As we can see, I've recovered the increased extinction near the midplane as we'd expect. And just comparing these extinctions to the values given by plugging in those stars' distances and positions, just comparing this to one 3D dust map, in this case BayStar 2019, we find a pretty good correlation between those fitted values and the 3D dust map. This is our sodium 1 map here, very similar looking to the extinction map with an excess of absorption near the midplane. But of course, these are just 2D projections when in reality they're 3D maps since we have distances to all these stars. So just starting at low or high galactic latitude, so 45 plus minus degrees latitude, we see a lower amount of absorption in sodium, but we can see how they start to trend with distance and calcium and extinction. Moving closer to the midplane, we see enhanced sodium absorption increased, and then all the way at 0 latitude, we see the strong correlation with distance and enhancement of sodium 1 absorption. So now applying this to one of our high velocity clouds, if we just zoom in on this little red circle here, we'll find the Smith cloud, which we can see has excellent coverage with our sample, over 1,000 stars within a 10-degree radius. This high velocity cloud has seen a lot of research done on it, including 3 distance estimates, 2 using indirect methods with gas kinematics and H-alpha fluxes, and 1 using a similar, as to what I described, high resolution stellar absorption study where they found evidence of one detection in one star of calcium K. And that's at a distance of 12 plus minus 1 kiloparsecs. Since then, Gaia distances have revised that distance of the one star with detection down to something more like 5 kiloparsecs. So it's worth revisiting the distance to this HVC. So basically what we do is we just plot this control sample here. So this is basically all of our stars at the same galactic latitude as our Smith cloud sample, so minus 15. And then comparing that to our Smith cloud sample, we can just compare the extinction, which is roughly equal. That's to be expected. Recent work studying dust depletion in the Smith cloud have shown that it's relatively low amounts of that, so it's not expected to be very dusty. Calcium-2, we see that it's systematically lower, but in sodium, we notice that in excess of distances of 1 kiloparsec, we see this excess in sodium absorption on the order of 100 to 200 milliangstroms, which may be indicative of a closer distance for that high velocity cloud. So to corroborate these results, I've also been conducting a high spectral resolution observational campaign with the 3.5 meter at Apache Point Observatory using the Archies shell, or about 35,000. I've obtained a spectra of about 36 stars covering the Smith cloud, and just comparing the equivalent widths that I measure at 0 kilometers a second LSR, so roughly corresponding to the interstellar absorption. The control sample is roughly commensurate with the peak of that distribution, and then comparing our Smith cloud absorption to velocities at the velocity of the Smith cloud, it's again roughly commensurate with that. And then just comparing the sodium-1 covering fractions, basically just the number of 3 sigma or greater detections of sodium-1 in both the SDSS sample and our high spectral resolution sample from Archies. We find that they're within the uncertainty of each other, so this may be indicative of a consistent covering fraction. So that's all I have to share for today, but I'm looking forward to refining these results and perhaps applying it to other HVCs. So thank you. I'd be happy to take any questions.
Really interesting. Thank you. I had a couple questions. One was explaining the calcium equivalent that was lower. How do you explain that? Is that I really like your strategy of having this control group. I think that's a great idea because I think it's tricky to model stellar lines in these strong features like sodium. How do you explain that?
Yeah, right now, I frankly think our sodium-1 measurements are more robust. It's a much more isolated region of the spectrum. Most of these are K-stars, so calcium-2. There's a lot of other absorption lines and a steep slope. So there's, I think, some refining I can do there to improve those measurements.
So what's your estimate for the distance? So it looks like it starts increasing slowly, pretty close.
Yeah, I mean, it starts right at 1 kiloparsec, which that's an order of magnitude less than the currently accepted distance estimate, but I think there's reasons to maybe doubt those previous studies. I mean, I want to continue corroborating with high-resolution data. We don't have, in our Archies sample, we don't have calcium because it's too low signal to noise. We are getting some later in the summer at Keck that hopefully we should be able to get the calcium absorption.
Okay, so I'm the previous studies. So it seems like you could go and get high-resolution spectroscopy of some of your target stars, right? And say, do I see the velocity very clearly? I mean, these are lower resolution, right? So,
Yeah.
Is that something that could be done? I mean, these stars bright enough with high spectral resolution?
So I tried. Most of these are like magnitude 17, which would require several hours of integration, which I might try to do this summer. But the ARCHIES sample I just selected from Gaia catalog. They're brighter.
Good stuff.
We'd be following in dubious footsteps, which is to say mine, if you were to try to do something with a high velocity cloud, enormous amounts of data, have some challenges, and then have great success studying the rest of the nodes away. High velocity clouds are just very difficult to study in this way and in other ways, and this is amazing work, but I guess a sodium sample of the 3D would be incredibly powerful for understanding the relationship between three-dimensional gas and these cooler tracers versus these warmer tracers. These are just super interesting. So I'm just very excited about this study, not just for real high velocity clouds, but for the whole rest of the galaxy. It should be really cool.
Sure, yeah. I previously, earlier in the year, I did try fitting the results to like a basic exponential model for just the sodium sample. That first attempt wasn't terribly successful. Probably the ugliest corner plots I've ever seen in my life. That's absolutely something that I'm going to talk about.
Okay, one last question from our co-chair here, Liz.
There's been some evidence, I think, of dust detection in the Smith cloud through depletion measures. I see that your AVs are not 0. Is there any way that you can kind of constrain the amount of dust or the AV in the Smith cloud with your measurements?
Yeah. So I know recently I read, I think it was Minter 2024, where they were measuring like OH in the Smith cloud. And I think they reported that the expected extinction would be on the order of like 0.03 mag, so pretty low. But there has been evidence of small amounts of dust depletion. Yeah, that's something that I'd be interested in.
Okay, let's thank Tim again. We can just, yeah, you can, yeah, we have a spare.
Thanks.
On really quick. Okay, just turn and you have this PDF, right?
Yeah, it's just
Okay, let me see if I can. Here. And then I have the time up here, and you can advance. Well, you can definitely point. You can advance this way. Yeah.
All right.
And you're on, right? You turn on. It should be green. Perfect. Okay.
All right.
Should I introduce you? Sorry.
If you want, I can also do it myself.
Okay, our next speaker is Alberto Saldana, who will be talking about extended Lyman alpha halos as probes of ionizing radiation escape near and far.
Yep. Thank you also. Let me introduce myself again. I'm Alberto Saldana Lopez. I'm a postdoc at Stockholm University. And I would like to thank the organizers for accepting a talk about the circumgalactic medium in high-radiative galaxies in a conference about interstellar medium. But I think if we aim to solve the multi-scale problem of galaxy evolution, we both communities have to work together, and I hope to convince you at the end of this talk that one can benefit from each other. So I'm going to talk about the extended Lyman alpha halos. So let's dive in. Need to use this one. All right. So first of all, what's the circumgalactic medium? I like to understand the circumgalactic medium of the outermost gas reservoir envelope between the ISM scale and the cosmic web. We know that the CGM is multi-phase, we know that it can trigger the gas in the CGM, can trigger star formation. It can regulate gas heating and cooling, and it also contributes to the metal mixing and the chemical enrichment of in the galaxy. So typical ways of observing the CGM is either in absorption. So we look at we take the spectra of distant bright sources such as quasars, and then we map some features on the quasar spectra appear in absorption. They came from intervening galaxies, and if we map these features with impact parameter, we can have a handle on the composition and also on the kinematics of the CGM. But another interesting way to look at the CGM is in emission, meaning that with techniques such as, for example, narrowband imaging or also integral field spectroscopy, we're able to map this diffuse emission at different wavelengths. For example, in the optical in O2, O3, magnesium 2, but also in the UV thanks to the Lyman alpha transition. And this is the main focus of my talk. There are different mechanisms that can contribute to the production of Lyman alpha emission extending beyond the starlight of the galaxies. But simulations predict that in the innermost circumgalactic medium, so below 20 kiloparsec or so, the dominant mechanisms is actually the scattering. So Lyman alpha photons are produced within the star-forming regions. They escape the star-forming regions, and then they get trapped into the H1 halo. They scatter many times, and they produce a Lyman alpha, extended Lyman alpha halo. So what do we know about extended Lyman alpha halos? So we know that they extend up to 10 times on average larger. They are 10 times larger than the UV starlight. And we know that the size of these Lyman alpha halos, they also scale with some galaxy properties, as for example, stellar mass. So now the question is, why do I personally care about Lyman alpha halos? Well, I care about them in the context of cosmic reionization. So we know that the universe underwent a cosmic phase transition, and it evolved from a mostly neutral state to a mostly ionized state at 1 billion years after the Big Bang or so. And we believe that the main drivers of this cosmic phase transition were galaxies, so ionizing photons escaping from the galaxy population. So one of the most pressing questions nowadays in galaxy evolution is to understand whether and how these ionizing photons really escape the galaxies. And in order to do that, so in the last decade or so, there has been a huge observational effort to really prove or to understand the properties that boost the escape of ionizing radiation from galaxies. So for example, we now know, thanks to observations, that galaxies with a highly ionized interstellar medium, as with very young stellar populations, they emit a high fraction of their ionizing photons. And we also know that the main two killers of ionizing photons, the main two sinks or absorbers of ionizing photons in galaxies are the dust and also the H1. And here where the Lyman alpha enters the equation. So Lyman alpha is proving ultimately the H1 gas within the galaxy, and some of the spectral properties of the Lyman alpha line, they correlate very well with the escape of ionizing radiation in galaxies. But as you can see, most of these properties, they have been studied at ISM scales. So I pose the following question on, do the circumgalactic medium conditions impact this escape of ionizing radiation? And in order to answer that question, we designed this survey called the Lyman Alpha and Continuum Origin Survey, or LA-COS. I forgot to put the links to the papers, but if you're interested, we published 2 papers. We put 2 papers on the archive on the 9th of April for some random reason. So you can check them out, please. So LA-COS is an HST large program where we observe 42 galaxies at redshift 0.3 or so. And these 42 galaxies, they all have previous observations with HST-COS at ionizing wavelengths. We target equally Lyman continuum emitters and non-emitters, so galaxies which emit a high fraction of ionizing photons and galaxies for which we don't detect any ionizing output. And we observe all these galaxies with the solar blind channel on board of HST. So we observe these galaxies in these two, with SBC in these two bands. These two bands are consecutive, so one of them at this specific redshift range, one of them is proving Lyman alpha plus UV continuum, the other one is proving only UV continuum. So we can subtract both bands, and we get a nice narrow band Lyman alpha. So the properties of our LA coast galaxies, they resemble the properties of high redshift galaxies. They lie on the scaling relations of galaxies at the epoch of reionization. So they are really analogs to cosmic reionizers. And this is how they look like. These are the color composites using the UV filters. So we see here we have pretty compact galaxies down here. We have some disk-like structures. We have some irregular dwarf galaxies. We have some multi-clamp galaxies. So the LA sample is really diverse, not only in terms of morphology, but also in terms of galaxy properties. And again, the main question of the survey was to answer this, this question. So do the physical conditions of the CGM traced in our case by Lyman alpha impact the escape of ionizing photons? And just visually, when we construct these Lyman alpha images, visually we saw that the Lyman continuum emitters, they seem to have a much more compact and Lyman alpha halos, whereas the non-emitters, they tend to have Lyman alpha halos which are more extended and also more diffuse. So this is represented here very simplistically with the sizes. So we measure here is the UV size, here's the Lyman alpha size. So we see that for equally compact equally compact galaxies in the UV, the Lyman alpha size is larger for the non-emitters, represented here with the empty symbols. We wanted to build on this, and we modeled the Lyman alpha halos using this two-component approach. So the first component, or the core component, is a Sgr profile, so modeling the Lyman alpha photons that are escaping directly from the star-forming regions. And then we have an exponential component modeling the halo, and these are the photons that came from the scattered Lyman alpha within the H1 reservoir. So thanks to these two decomposition to component modeling, we have access to the real size of the halos, as well as some other properties, as I will see now. So we see that the Lyman alpha, again, the Lyman alpha size, the halo size is 10 times farther than the UV size, in agreement with high redshift galaxies. And these pose the question of whether there is a lack of evolution of the neutral conditions of the CGM with redshift, because we see the exact same properties of high redshift halos. We also discovered some correlations between the scale length of the halo and other galaxy properties, for example, the O302, meaning that the highly ionized galaxies, so high 3O2 galaxies, they have also less extended halos, or in other words, galaxies with more neutral gas on them, so galaxies in which the equivalent width of the H1 is higher, they have more extended halos. But we wanted a quantity that can encapsulate all these properties of the halo together, and for that we use this metric called the halo fraction. So the halo fraction is just the luminosity of the halo divided by the total luminosity of the total Lyman alpha luminosity of the galaxy. And what we discover is a nice correlation between this halo fraction and the escape fraction of ionizing photons. This is the main plot of the paper, and it means that, again, it corroborates what we saw visually in the previous slides. So galaxies with high escape fraction of ionizing photons, they have low halo fraction, meaning that their halos are small and compact, while galaxies with low escape fraction, they have high halo fraction, meaning that the halo is more extended, more luminous, and more diffuse. And this is in agreement, this result is in agreement with simulations, and it's always a relief when your observations agree with the simulations. This nice work by Nikolai Chausikov in 2024, they saw exactly the same thing using Sphinx hydrodynamical simulations, and we corroborate their predictions. We also find this a correlation between not only between the halo fraction and FSK, but also the halo fraction and the equivalent width of the H1 lines. So we build up the following physical picture. For Lyman continuum emitters, for non-emitters, so galaxies in which the escape fraction is low, what we see is that these galaxies are usually surrounded by a high column density of neutral gas. That means that the ionizing photons, here represented in blue, they get absorbed within the ISM, and the Lyman alpha photons, they scatter out of the line of sight, and they produce a bigger halo. On the other hand, for Lyman continuum emitters with high escape fraction, there is no such a H1 screen between the stars and the observer, and therefore the Lyman continuum photons and the Lyman alpha photons, they escape directly from the central star clusters without suffering any absorption or any scattering in the case of Lyman alpha, and therefore their halos are shallower and smaller. I'm not sure how much time do I have. Who is the juror? Oh, is there 1 minute? So I will read the conclusions now. Fine. Yeah, here are my conclusions. So we know that the innermost circumgalactic medium, the dominant process for Lyman alpha emission is the scattering of Lyman alpha photons. Our LA coast galaxies show extended Lyman alpha emission ubiquitously. However, the Lyman continuum emitters, they show more compact Lyman alpha morphologies. And then by modeling the halos with these two component modeling, we discovered that there is a tight correlation between the halo fraction, or the contribution of the halo to the total Lyman alpha luminosity, and the escape fraction of ionizing photons. We build up this physical interpretation, and finally, we argue that our relation between the halo fraction and the escape fraction can be used to can be applied to high-redshift galaxies where we do not have access to any ionizing output information. Thank you. I'm happy to answer your questions.
Thank you for the great talk. I noticed, so you mentioned your first conclusion point is that Lyman alpha emission is in the inner CGM is dominated by the scattering process, but what about the outer CGM? I noticed in the slide where you have many of your samples, and oftentimes the outer CGM can be asymmetric and have all these weird funky shapes. I wonder if you can make any comments on this, or if
right. So so this is a conclusion from, this is not a conclusion from my work, but from simulations. And the point was to say that our observations are not deep enough to prove the outer CGM. These are relatively, not shallow, but relatively modest observations. So we only prove the CGM close to the ISM, let's say. So that was the point. I cannot say anything about outer CGM scales.
Do you know if any of your targets have observations in, say, Muse or something to get more of the optical spectra of some of these other emission lines you used?
Yes, so we have Muse for some of our galaxies. The problem is that our galaxies are so compact. These are very compact galaxies. For Muse, we need to use the AO system in order to resolve some structures, and the AO system, the wings of this, how's it called, the Strel radius is too, it doesn't go too far beyond the ISM. That's the problem. Yeah.
Thank you.
Other questions?
Yeah, I was wondering how the halo fraction, if you know, if it correlates with other galaxy properties like star formation rate, formation efficiency, and even molecular gas data, that sort of thing. Is it being driven by the processes of the central galaxy or by external?
That's a good question. I don't remember if it correlates with the halo, with the galaxy mass. I would say so, but it correlates with the O3O2, with the equivalent width of H beta, with the equivalent width of the absorption line, with metallicity as well. But I don't remember right now with the galaxy mass or star formation rate. But I can come back to you.
Really cool talk. So you talked a lot about Lyman continuum escape fractions on galaxy scales. So I'm wondering if you have thoughts on what this escape fraction looks like on individual star forming region scales.
No, we don't have access to that information because all of our escape fraction measurements, they came from COS. So COS has a 2.5 arc-second aperture, right? So 2.5 arc-second will be like that. That means that we don't have resolved information about Lyman continuum, but it could be great.
Any other questions? Okay, let's thank Alberto again then. So you're all mic'd up and your mic's on?
Yes, I think so.
Yep, it sounds like it's on. And
Great.
Then here you go. Oops. Okay, so here's it.
There's a laser, yes.
And I'll put the time on.
Great.
Okay, our next talk of the session is by Christiane, who will be presenting gas, dust, and H alpha over fraction alpha decrement extinction of stellar associations in NGC 4826 with.
Great, thank you so much. My name is Chris. My name is Qiu Shitian, but I go by Chris. I am a post-bac research assistant at Johns Hopkins, and I'm very happy to talk about this project. It's a great flow that we just talked about alignment alpha, and now we're going to Balmer and Passion. I have been working at Johns Hopkins for a year. I graduated from Wesleyan University last year, and Seth Redfield, who just gave a talk this morning, was actually my undergrad advisor. We work on exoplanet together. I think this is my first time I'm showing him the work I do after I graduate, so it's a huge honor. And I also want to take this opportunity to thank all of my mentors, advisors, like Seth or Kirsten Larson, Dave Thilker, Janice Lee for this project, and also Christina Lindberg is my peer mentor at Johns Hopkins, and so many other people. I could not have done this without all of your support and help. So thank you so much at the very beginning. This project obviously is a FANGS project. So what is FANGS? FANGS. FANGS. So FANGS is a survey of physics at high angular resolution in nearby galaxies. So this is what we call the baryon cycle. Basically, dust and gas form stars, and then supernova explodes. Things go back to gas and dust, and then we form stars again. But there are so many things happening in between this cycle, and we want to have a whole picture. So we have multi-wavelength, multi-observatory coverage from ALMA to VLT Muse to HST, JWST, and even more instruments. And we are a very large international collaboration. I work with the stellar population group here. So my starting point is from a stars view. You might have seen many of our very pretty pictures, including one that you can grab right in front of the front desk. Hopefully we haven't run out yet, but that one just became a priority mail post stamp. So if you ever want to get the $10 mail, you can get one of those. I'm sure your friends will be impressed. Many of us works on ISM or adjacent to ISM. So we have a lot of people giving talks and posters here. Just remember to check them out. Many of us are early career researchers like me, so we would be really appreciative if you can come talk to us. Sorry, it's a really long introduction. Here, I start to get to the exciting part. If you look at this cutout of an image in one of our galaxies, you can see a lot of stars, and there are a lot of clusters that we normally spend a lot of our energy on. Those markers mark star clusters. We all know star cluster. They're well-defined. You can study the age, the mass of them. But then you realize there are many more stars that are not in those star clusters. Those are what we have in FANGS stellar association, or multi-scale stellar associations. So we trace them with individual stars. And as you can see, it fill in a lot of the blank space between the clusters, and it provides a more holistic view of the stellar population in a galaxy. If you remember from Professor Bob Benjamin's talk, it's a very similar idea, except that these are made of individual stars. But they could, as you can see, some of them do include a cluster inside. This is why it's fun, because we're literally looking at a space that's interstellar. And my talk, one of my goals is to prove that by only looking at the stars, you're missing out a whole lot of information. So we really need this information interstellar. And this picture you're looking at is actually from a galaxy, Messier 64, where we always use NGC 4826. It's called Evil Eye Galaxy or Black Eye Galaxy because of this very prominent dust lane over here. And this is not just what it looks like. People have suspected that there might be a previous merger history, and there's a counter-rotating gas disk beyond what you can see here. So this is a very special galaxy, and it's also one of our closest galaxies. So we can have very great resolution. It's a perfect study for my project. So as I said, we're mostly working with stellar populations. And a lot of things we do is that we plot a color diagram like you see here. So basically, both of the axes are color. The horizontal axis is the V minus I color, and the vertical axis is the U minus B color. And this track, you can see here, is actually a stellar evolution track. So if you have a stellar population that's young, it's up there, and then it goes down this track. And then you can also see that I have some contours here. That's the average distribution of stellar associations in Fang's sample. And then this galaxy, the stellar population is really different from our average distribution. And this sort of poses a challenge because you can see here there's a reddening vector. So if you have dust, it will redden the stellar population in exactly this direction. So if we have something like around here, you can't really know if it's actually from here or if it's actually from there, but with a greater dust extinction. This is what we call the age reddening degeneracy, and it's a big problem. You can't really tell without other information, but luckily we do have other informations. Here is a 3-panel view of optical light and also H alpha and Paschen alpha. They're both in the red band. So with this, we can, just like Balmer decrement, derive extinction. So this is an extinction map. And it's even better than Balmer decrement because Paschen alpha is like a longer wavelength. It's less obscured by dust. And you can see this huge dust lane that you see here in optical wavelength is almost transparent in the JWST color image. So with this dust extinction map, there's so many things we can do, but one of them is to measure independently the dust extinction of all of my stellar association regions. Here they're compared with the measurements of extinction purely from SED fitting. So SED fitting is basically using the same color diagram. So it will be subject to the age reddening degeneracy. So if we use our derived extinction to correct for these stellar populations, you can see that they go back to the younger range of the stellar evolutionary track. And then some of them might be overshooting a little bit. There's obviously noise and so many other interesting things going on. Yeah, but so this is all of the stellar associations in this galaxy. But we really want to look at things more in detail. So we want to also have a little bit of view of each individual associations. So here you can see in H alpha or Paschen alpha, they're both in the red band. There are many things that you can notice. So for example, there's visibly more dust obscuration in the H alpha color image. But there's also one more interesting thing is that the morphology of the H2 emission is very different. Like this top panel, you can see it's very localized. There's only like one or two stars or clusters or clumps of H2 emission. And then the middle one is more of like a diffused but constant uniform H2 emission. And the bottom one, you sort of see a clearing at the center, and then there's H2 emission around it. So they are different degree of coverage of H alpha and Paschen alpha. And this is very interesting, especially when we see something like this. Is it because the stellar feedback or previous supernova, is it actually blowing things out? So we want to, instead of just looking at pictures, we want to quantify this a little bit. And one of the ideas I came up with is to use something that's very familiar to a lot of the extragalactic astronomers, which is a Gini index. People have been using that for galaxies as a whole, but I'm thinking maybe I can apply that to my individual stellar association regions too. And there's another thing, which is what I call a covering fraction, but I think everyone has their own version of covering fraction. But basically, it's using the cumulative flux distribution. So it's more like a localization index. So I've tried these two methods, and they're agreeing really well. If you're not familiar with Gini index, a 0 of Gini index is basically uniform, and the cumulative flux distribution is sort of goes the other way. So as you can see, there's a negative correlation, and it's basically pretty spot on. So I'm just gonna use one of these two, and it will convey the same idea. So let's look at a few more regions in detail to see how this idea is working. For example, this one, so it's H alpha on the upper left and Paschen alpha on the lower right. This one obviously is pretty uniform, and apologies for the plotting, it's a little weird, but as you can see, it has a Gini index close to 0 and a large covering fraction, which means it's more covered and it's more uniform. And basically, this is how we obtain this covering fraction from the cumulative flux distribution. This is like how, by pixel, how the flux grow within the region. As you can see, it's a pretty constant grow, and then it reached 1 or 100% of flux. But you can have another region that's, obviously there's a clump in the center. So this one is very localized, it's not uniform. And then you see a higher Gini index, a lower covering fraction, and the growth curve is a little bit weird. There's a little turn there, and then it suddenly grow a little bit. That's because of the clump. So we think this is working really well, but that's not the end of the picture yet. If you remember from our first talk from Dr. Greg Green, there is something called polycyclic aromatic hydrocarbon, but we just call that PAH. And that is basically dust particles that's emitting light. So it's very different from the H alpha to Paschen alpha decrement, which is tracing dust extinction. This is directly imaging dust emission. And we want to compare them because as Dr. Greg Green has already mentioned, there's a weird correlation and relationship between extinction and PAH. And they're both driven by excitation or ionization. So on larger scale, you can see that they sort of trace each other. This is a 3-color image in H alpha, Paschen alpha, and PAH. You can see mostly it's tracing each other, but if you really zoom in, you can see that here's another bubble-ish thing, and here too. And then you can sort of see the H alpha and Paschen alpha emission is a little bit more inside of the PAH emission. We're thinking maybe this has something to do with the excitation or ionization energy required, or there's different reaction of gas versus dust to stellar feedback. And they are actually a perfect stellar association inside those. So this is not just a coincidence, that this is indeed has something to do with the stellar population inside. I am trying to get to the end, but instead of just quantifying H-alpha and passion alpha coverage, we can also include PAH. And here, this is really interesting because this one, the PAH doesn't agree with H-alpha or passion alpha. And it seems that you can't just explain this with blowing out a scenario or different level of energy requirement. And also the Gini index versus covering fraction relationship is really wacky for PAH. And this is gonna be my future work among many others. And we're trying to publish a paper by the end of my post-bac, so stay tuned for that. Here's a summary, and you can learn more about me or my project at my website, or you're welcome to reach out to me. Thank you so much. It's my pleasure to present my work here.
Thank you so much. Questions?
Great talk. I had a question. So this is a very inclined galaxy. So I was wondering how this impacts the completeness of your stellar association catalogs, for example, or do you correct for these information points?
So I'm not, it's generally, I would still say this is pretty much face on. It's not like an edge on galaxy. I mean, it's not perfectly face on, but it is what we consider face on. You know, if all of the stellar stars are living in a disk, and we assume the disk is pretty thin, then I don't think that should be a big problem. I haven't looked at any possible correction for the inclination, but I don't think it will be a big problem.
Other questions?
So when you go back to your color diagram, Chris, the color diagram that you were showing, where is that complete to? Do you know?
Oh, this is a great question. Well, towards the redder end, well, so on a color diagram, you sort of can't see the magnitude or the luminosity, but I think towards the red end, some of those points might have larger error volume. It's not as straightforward as, you know, a color magnitude diagram, but yeah, completion is a factor here.
Do you think maybe like 100 million years or something? A couple 100 million years?
Let me see if I have the, I think it can go a little bit more than that, not just 100 million year. This is a great question. It also depends on, I mean, I know that in our collaboration for clusters, it can still be pretty reliable at even a giga-year, but for stellar association, it's definitely lower. So I would say probably between 100 million year and a giga-year, something like that.
I love that. Thank you.
Thank you so much.
I agree where you have the star cluster and then the H alpha and as a ring. Yes, probably feedback is doing that almost certainly. We've been seeing stuff like this in the Milky Way for a while now. And the great thing about JWST is we're starting to see morphologies that have become familiar to us in Spitzer surveys, for example, in the Milky Way and H alpha surveys. We now see this reproduced in galaxies like yours. My question is, you didn't quite say, but I assume that when you do the de-reddening on the slide you're just showing, you're really just using the decrement and not the SED information, or do you have a way to use the information from either one? Like if you see some point that seemed overcorrected, could you maybe use the other measure to compensate for that?
Yeah, that would be a great idea. In fact, we do something like that similarly in our collaboration for clusters. Here, what I'm showing is purely from the decrement. I'm not using the SD information at all. And I think we're intentionally trying to keep them separated at the beginning, just so that we can compare them and understand maybe the overcorrection or the systematics in that. But later on, I can definitely see there could be a way that both information into this, and that will be helpful and more reliable. I agree.
Okay, we have a question online.
Yeah, it was sort of related, Chris. Bauman Karimi asks, what about using the Whitmore et al. 2025 method to produce SED templates of the star clusters?
Yeah, that would be that would be a great idea. So in general, I think it could work, but like I said, clusters are so well defined, and I'm not exactly sure what Brad did, but he might have used more of well, clusters in general, they are very regular, and you do it with a circular aperture. But these you can see, they're not circular or well organized at all. And then there's also different covering and things like that. And another thing here is underneath this purple line, there's a little bit of purple dots. Those are a stochastic model, which is not assuming a uniformly sampled AMF. So there's a little bit more nuance there. So even SED template might not be able to distinguish the stochasticity well. So I guess it should be feasible, but we'll need to look more into that.
Okay, so one last question. While Marjorie, you want to come up? Who wants the last question? Chris?
Sure. It's on the right slide for me. So this is, I'm very interested in the difference between the SED-derived AV and the Deckerman-derived AV.
Yes.
On a Lincoln sightline, the difference between those two tells you something about geometry, like what's clumpy versus screen-like, which is interesting, again, if you're care about covering fraction type things. I mean, Carl will probably say more about what that actually means, but there's radiative transfer information in the difference between those two AV measurements, which might also be useful for your covering fraction.
Yeah, I think that sounds definitely right.
Actually curious, have you explored this yet?
We haven't, but I think that will be on my to-do list. So thank you so much for bringing that up.
Okay, great. Let's thank Chris again.
Yes.
Okay, and our last talk of the day and of today's session is by Marjorie de Clare, and she will be presenting MEAD, Measuring Extinction and Abundances of Dust.
Okay, hello everyone. As Katrin just said, my name is Marjorie de Clare and I'm an ESA Research Fellow here at SDSCI. I want to thank the organizers for giving me a chance to talk about the MEAD project, which stands for Measuring Extinction and Abundances of Dust. I realize I'm between you and drinks, and it's been a very long day, so I will try to keep this as light and as entertaining as possible. Okay, let's start. Okay, this doesn't work. As the name suggests, MEAD stands for Measuring Extinction and Abundances of Dust. And the ultimate goal of the project is to better understand the properties of the dust grains in the Milky Way. So I will first talk about extinction and what we can learn from extinction measurements. Then I will move on to the abundance measurements. And at the end, I will tell you how we can combine the two to learn more about dust grain properties. So first, extinction. We already heard quite a lot about dust extinction today. But just to make sure that we're all on the same page, extinction is a combination of absorption and scattering from light, of light, for example, coming from a star, by an intervening medium, for example, a dust cloud. And if you want to study an object that is obscured by dust, whether it's galaxies or stars or supernovae or whatever you are interested in, sooner or later, you have to deal with this dust layer. And it is therefore really important that we understand how the dust affects the starlight and how we can accurately account for dust extinction. So I realize that for most of you, or many of you in this room, dust extinction is a bit of an annoyance, something that you're trying to get rid of, preferably as quickly and as easily as possible. But today I will try to convince you that the dust extinction is actually very useful, Because we can use it to learn about the properties of the dust grains themselves. So here I'm showing an average extinction curve for the Milky Way. You've seen one of these already a couple of times today. And so extinction is very wavelength dependent. It's high at short wavelengths, and it drops as we go to longer wavelengths. So this is very interesting because we know that smaller grains are more efficient in absorbing light at short wavelengths, whereas larger grains are more efficient at longer wavelengths. So different wavelength regions give us information about different sizes of dust grains. And the overall slope tells us something about the distribution of the dust grain sizes. And on top of that, we can also observe features in the extinction curve, such as this very strong feature at 2175 angstrom. And features like these are interesting because we can compare them with laboratory measurements to reveal the composition of the dust grains. For example, we know that the UV bump is caused by some type of carbonaceous grains, and the 10 and 20 micron features are caused by silicates. So, as I mentioned, extinction curves are very useful not only to account for dust extinction in all kinds of observations, but more importantly for my research, to better understand the properties of the dust grains, such as their size and composition. And with Webb, we can now study the infrared part of the extinction. So as part of MEET, we obtained Webb spectra for 9 OB stars in the Milky Way with the NIRCam GRISM and the MIRI MRS. And so you can see the spectra on the right, they look very nice. So it's important to note that all of these sightlines have relatively low amounts of dust extinction with AVs between 1.2 and 2.5. So we're really probing the very diffuse interstellar medium in these sightlines. So from the spectra, it's immediately clear that we have a clear extinction feature at 10 micron in all of the sightlines. So this is, of course, the silicate feature. And we know that this feature is caused by the stretching of the silicon-oxygen bond in the silicate dust grain. Now, with the high sensitivity of Webb, we cannot just detect this feature, but we can measure its detailed properties, such as its strength, its central wavelength, and its width. And we know that these properties depend on the properties of the dust grains, such as their size, their shape, their composition, and so on. So really, if we can study the feature, we can learn something about the properties of the dust grains. So as I said, we see the feature clearly in all of the sightlines, and we fit the feature with a skewed Gaussian, which is indicated by the red line in this plot. So this fit gives us the detailed properties that I was just mentioning, right? The strength, central wavelength, and width. And interestingly, we see quite a bit of variation in these feature properties between the different sightlines in our sample. So this means that the silicate dust in our sightlines is quite different between the different sightlines. More specifically, the strength of the feature tells us how much silicate there is, and the shape gives us some clues about the type of silicates that we're dealing with. So to better understand these variations, I also compared the silicate feature properties with other sightline properties, such as the V-band extinction, the hydrogen column density, and the V-bump strength, and so on, to find correlations between the silicate feature and these properties. Now, I don't really have time to talk about these, but if you're interested, you can ask me afterwards, or you can check out the paper. So one more thing to note on this plot, maybe you've been wondering what the extra feature is on the long wavelength tail of the main feature. We don't actually know. There's a long list of candidates. It could be silicon carbide, it could be crystalline silicate, it could be PAS, it could just be an artificial instrumental feature. So we're still trying to figure that out. Okay, so that sort of covers the silicate dust, but what about the carbonaceous dust? Can we learn something about that from our Webb spectra? Well, in the near infrared, there are features caused by carbon dust. However, in our individual MEET spectra, the signal-to-noise ratio at these wavelengths is not high enough to really claim a detection in each of these sightlines. But if we average all the spectra, we do detect a feature at 3.4 micron. And this feature is caused by the stretching of the carbon-hydrogen bond in aliphatic hydrocarbons. And similarly, we detect a feature in the average spectrum around 6.2 micron, which is caused by the stretching of double-bonded carbon in aromatic hydrocarbons. So again, we're kind of limited by the signal-to-noise ratio here, and you see some systematic peaks in the data. But if these features are real, this would be their first detection in these very diffuse sightlines with AVs below 2.5. So that means that hydrocarbons exist in these very diffuse environments. But then there was another feature that really caught our attention in this specific sightline, HD 73882, around 3 micron. And this feature is likely caused by the stretching of oxygen-hydrogen in water ice. And also in the average spectrum, we see some sort of a feature around 3 micron. So that is a bit mysterious because it is generally believed that water ice can only form and survive in dense molecular clouds. But these are very, very diffuse sightlines. So we're not actually quite sure why we detect ice in these sightlines. However, recently there's been some new laboratory evidence and also theoretical work that claims that a few monolayers of ice can actually exist in the very diffuse ISM. So again, we're limited by the signal-to-noise ratio here, but if these features are real, this is the first detection of water ice in very diffuse sightlines with AVs below 2.5. And that means that we still have a lot to learn about how water ice can form and exist in very diffuse environments. Okay, so extinction features tell us how much of certain types of dust grains there is, and also gives us clues about the properties of these grains, like their shape, their size, and the composition. So now moving on to the abundances of dust. At this time of the day, I don't want to throw any equations at you, so just in words, we measure the dust abundance of a certain element by starting from a reference total abundance and subtracting the observed gas abundance for that element. So basically, this translates to how much of a certain element is locked up in the dust. And that tells you something about the composition of the dust grains. So to measure these gas abundances, we took spectra with the Hubble Space Telescope for our sample of sightlines, and we used STIS to get really high-resolution spectra. And then we measured the gas column densities from the gas absorption lines in the UV spectra for magnesium, iron, and oxygen, which are really important components in the interstellar dust. So to recap, extinction features tell us about the quantity and the properties of the dust grains, and the abundances tell you exactly which building blocks and how many are available to build your dust grains. Now, what if we combine that information? Can we learn something more? Well, let's see. Yes. So here I'm plotting the peak optical depth of the silicate feature against the column densities of magnesium, iron, and oxygen in the dust. So just to remind you, this is really the strength of the silicate feature versus the number of atoms of these elements in the dust. And we find an almost perfect correlation here. So this is consistent with this feature being caused by silicates that contain magnesium and iron, such as olivines or pyroxenes. So we kind of already knew this, but this is the first time that we can observationally confirm this without needing any laboratory experiments or any dust grain modeling, just by comparing extinction and abundance measurements for the same sightlines. So that's kind of cool. However, if we fit the data with a line, we find a non-zero intercept. We find a small positive value. And that means that if we extract the line to 0 column density for magnesium, iron, and oxygen in the dust, we would still measure a small silicate feature. Weird. So we have a few ideas why this could be. For example, maybe we shouldn't be assuming a linear relationship here. Or maybe we're limited by the small sample size. Now, doesn't that sound like a great idea for a JWST proposal? We thought so too, and so did the TAC. And I'm happy to announce that we will get 25 additional sightlines, so 25 more data points on these plots, which will hopefully clear things up. And with that, I'm at my summary. So with MEAT, we're measuring extinction and abundances of dust for the same sample of sightlines. And the goal is to really learn more about the properties of the dust grains. We find a strong silicate feature in all of our sightlines, as expected. but also tentative detections of hydrocarbons and even water ice in these very diffuse sightlines. There's a strong correlation between the strength of the silicate feature and the column densities of magnesium, iron, and oxygen in the dust. But when we fit the data, we find a positive intercept that we don't really understand yet. However, soon we're going to get new MIRI data to hopefully clear some things up. And with that, I'm ready to take questions. Thank you.
Yeah, hi, great talk. I was just wondering, like, wouldn't you expect a positive intercept because the dust would be more than just magnesium silicate or just iron silicate?
Yeah, I mean, in general, the dust is, of course, more than magnesium, iron, and oxygen. But the silicate feature, which is really what we're plotting on the y-axis, is okay. The silicate feature is believed to be caused by silicates, right? And silicates are usually containing magnesium or iron. There's also silicates that don't contain any of these, but they always contain oxygen, right? Otherwise, it's just not a silicate. So with these data, we find that even if you don't have any magnesium, any iron, and any oxygen anymore in the dust, the feature is still non-zero. And so that's the thing that we don't, quite understand. But there's a lot of assumptions going on, a lot of systematics. So hopefully with the new data, we will understand what's going on here. Yeah.
Yeah.
Thanks for the great talk. This is really exciting and important work. For these abundance calculations, how much do you worry about your assumed total abundances?
A lot.
Yeah.
Yeah, there are many different values out there. However, I have to say that I tried a bunch of them. I actually tried the range that is in the literature, and I still couldn't get to zero. But yeah, it might just mean that, we still don't get them right, even though we have all range in the literature. So.
I was wondering, what you know about the different environments that you're probing with these different sightlines. Like, are they all just diffuse ISM, not close to any stars, or do they have
Yeah, so they all have very low AVs, so they should all be very diffuse. And so we're using OB stars as the background stars. But they're all scattered in the Milky Way. We're not aiming at a specific direction. But I haven't actually, I should probably compare with 3D dust maps to see if there's anything special going on for these specific sightlines. But yeah, I can also say that their UV extinction curves look very average. Yep.
Okay, Greg, then Seth, over here. Yep.
So there's an alternative method of getting the depletions that doesn't depend on our reference, right? That I think it's from Jenkins 2000 something. Looking at the relative depletions, how quickly different elements deplete, and then using that to get the total amount of depletion. Have you tried that?
No, not yet. So we were really trying to get the absolute depletions in this case, so that we could compare them with the features. But yeah, we can try the relative ones and see what that gives us as well. But there's then other assumptions that go in there. So
sure, yeah,
it's
a different set of assumptions.
Yeah, exactly. Yeah, it's a different approach, but I can try that.
You look at the ratio of the pyrrocene to olivine. In the local ISM, we see a lot more olivine.
Right. So I did look at ratios between the abundances. And actually, I used the slopes that you can see to measure the stoichiometry. And so we find that there is a lot more oxygen to begin with than can actually go in the dust. So that's another problem. But also the ratio between magnesium and iron is different from what any dust grain modeling models predict. And I think I might have an extra slide for that. Not there, not there. Uh-oh, I broke it. Anyway, I can show you later, but yeah.
Thank you.
Thank you for the great talk. I was wondering if you could say the trends you find here, how applicable would they be if you went to higher redshift? Would you expect to find the same sort of things at, you know, high redshift galaxies? Not super high redshift, but, you know,
Right.
0.51 something.
Yeah, so like in other galaxies than the Milky Way, basically. I think the only galaxies for which we have depletion measurements so far are in the Magellanic Clouds. And so I'm afraid that's about as far as we can go to actually measure this. But there are indications that dust is different in different galaxies, of course. So I don't really know how this would translate to the high redshift. That's a good question.
Any last quick question for Marjorie?
Okay, yeah, go ahead.
Okay, the last three profiles, oxygen, magnesium, and iron. The initial point, the first point is low in all of them. Is that covariance in the measurements, or is that hint that things are dropping?
Yeah, it's probably just an outlier, but it's true that we don't have information at these low column densities, and that's what we focus on the proposal. So most of the new data are going to be in the lower part of this plot. So yeah, we'll see. Yeah.
Okay, let's thank Marjorie and all of our speakers. What an awesome first day, everyone. Can we just do one big round of applause for all of the talks and posters? We now have our conference.
Well, before we have the conference reception, long list of people being thanked. The two people who deserve the most thanks are absolutely Liz and Shemaya, who have done terrifying amounts of work for this, some that wasn't originally planned, and so they have extra large thanks from all of us who were ably directed and helped by them. So we want an especially large round of applause for Shemaya.
So who wants a drink? We have our reception outside in the cafeteria with a bar. But while you are mingling and chatting with your colleagues over a drink, I would encourage you all to look at the discussion whiteboard and vote on discussion questions that are interesting and add discussion questions you want to talk about.
You want 125 tally marks.
Please, if you add a discussion question, we would strongly encourage you to add your initials so that you can volunteer to lead this.